Hello, and welcome everybody to Coffee with Cluster One. I'm Sven, and I'm going to be your host for today. I hope you have a coffee or a tea or some other beverage with you and you're sitting comfortably, because today we're going to have an exciting speaker for you. Jussi Karlgren is an expert in computational linguistics, and he's an adjunct professor at the KTH in Stockholm, Sweden. He's also a founding partner at the text analysis company Gavagai. And today he's going to talk about how to build a learning lexicon from streaming text. Today's session will take around 1 hour. Jussi will speak for maybe about 40 minutes or so, and then we'll have a question and answer session. So please, if you have any questions during the talk, feel free to write them down in the chat box. We'll collect the questions, and then Jussi will answer them after the presentation. Before I give the stage to Jussi, let me introduce you to Malo Marek, our co-founder and product strategist here at Cluster One. Malo will give you a short intro to what we do at Cluster One and how it can benefit your work, and then we'll move right on to the talk. All right, Malo,
awesome.
You've got the mic.
Great, I'm glad to be here and to hear what Jussi has to present today. First of all, I'll just say a little word about Cluster One and what we do. We're created with the goal of making running AI at scale very easy and making AI research and development easier and more efficient and faster. So we were founded in October 2016 and launched in August 2017, and we recently raised our seed round with the Allen Institute for Artificial Intelligence, Paul Allen Foundation. What we try to do is make AI and deep learning research faster by enabling everybody to take advantage of the scalability of the cloud or managing their on-premise machines and running distributed training to speed up model developments. So all about speeding up research cycles through having the right infrastructure. We enable a zero DevOps platform, meaning that data scientists don't have to waste time on setting up infrastructure to run their experiments, and they can just plug and play. And we are also infrastructure agnostic, meaning our platform runs on top of any of the clouds or on-premise, freeing people from the constraints of choosing a cloud or choosing where they need to run their experiments. So the way this looks is we have a platform that supports any deep learning framework or what you could call apps, so TensorFlow, PyTorch, Caffe, and some tools such as Jupyter Notebooks, TensorBoard, etc. And we give access to that through a CLI, a graphical user interface that's built for collaboration, etc., etc. And what we do is we abstract away what we could call the operating system part and the management of the infrastructure part from the data scientist. So orchestration, access control, monitoring and optimization, and the overall management of the infrastructure is taken care of. And this platform can run on any source of compute, AWS, Azure, GCP on-premise, connect to any storage to minimize wrangling, so S3, EFS, NFS bounds, etc., and read from any code artifact wherever your code is. And so that gives a lot of flexibility without needing to think about the underlying infrastructure. So now I'll just hand it over to Jussi. Jussi, if you want to share your screen.
Yep, coming up. There we go. We should get it there. Are you seeing my screen now?
No, not yet. You probably have to do it twice again.
I'll try to do it. Stop share. This is an artifact of Zoom combined with Ubuntu. Let's see. Share screen. Oh, hang on. That's the one I want to share.
Yes.
Okay, wonderful. Hello, world. Good to have you all here virtually. I am from Stockholm, and you're presumably scattered here and there over various time zones. And this is soon dinner time here in Stockholm, so this is a good time to end the day and talk about big thoughts and big things. And some of you are at your morning coffee, I guess. So, which is also a good time to do all kinds of thinking. So this is about how to build a learning, let's see, back to the title, how to build a learning lexicon, which is what we call what we build from the language resource we build from streaming text. And I'll say a few words about how we use it and how and why we're doing it the way we do. Myself, I was already introduced by Sven. Thank you for that. I've worked with various things related to information access and information retrieval from a linguistic standpoint during the past 20 years or so. And what I will be presenting now is largely a work of myself with my students and most importantly with Magnus Dahlgren, my colleague and previous PhD student who I started the company Gavagai, or founded the company Gavagai with about, 7 or 8 years ago. Gavagai is a text analysis company based on research. Originally, it was entirely research-driven, but it's been more and more interested in building stuff that actually people use. And what we do mostly today is build what we call the Explorer, which is a text clustering thing, which I strongly encourage you to look at if you have plenty of stuff you need to cluster. It's quite useful. We also do media monitoring, although that is a lesser business, seeing what people are writing about your brand or idea or major thing. And we produce a backend for both those services, which is also available for people who want to play with it. And you can go there. There's a free demo or a free web interface at that URL right there to see what sort of things I'm talking about once I've given you the background here. This is all based on the general idea that linguistic resources should be learning rather than defined beforehand. When we started out doing this was a contentious issue. It is so no more. People now, have largely accepted the fact that given the variability of human communicative behavior, it's a good idea to build things that learn from how people express themselves rather than use a predefined dictionary, which will give you the ways people ought to be, in some sense of the word, expressing themselves. Simply put, if you want to, trawl social media or informal text in any way, standard resources won't cut it. People don't write the way their grade school teachers taught them to do, so the systems we build need to accommodate that. This graph here is a testimonial to my graphing abilities, but it gives an important thing. You see the blue line right at the bottom and how it actually increases over time. This is the number of new words you need to read the newspaper every day. You cannot quite see at the very left corner in the graph. At the first day you read a newspaper, there'll be plenty of new words. And the second day you read a newspaper, there will be plenty of new words again. And that curve sort of flattens out after a few days, but it still keeps increasing. And after 2 years of reading the newspaper every day there'll be a dozen or so new words. There'll be a new person elected somewhere in some place you haven't heard of before, and a new invention. Someone invents the internet or a modem or something. This is news text from the mid-90s, and the steep growth of that graph, which is hardly visible in this picture, was what motivated me to start thinking about learning algorithms. You're never done with learning a language, even if it's your first language. These happen to be English language newsprint. It's the Glasgow Herald and LA Times, read by a Perl script every day for 2 years. And it just keeps growing. Every day there are some typos there as well, but this is pretty well-structured text written by professionals, intended to be, sustainably archival quality of the material. This is back in the mid-90s when text was proofread really carefully before it was published. Now, the red is the same graph for tweets. There are several orders of magnitude more new tokens every day, hundreds of thousands of new words, new items every day. This is only English language tweets. And that said, those are tweets, microblog posts that are mostly in English, but they contain a lot of other languages as well, because people use all kinds of mixes when they talk about things. There are jokes, many misspellings and typos. But new words, new ideas, hashtags, all kinds of humor and human creativity right there. And you cannot really disregard all that signal by using a standard dictionary and throwing out words that are not in vocabulary. So that's a good motivator for thinking about how human language processing works. Human information processing is really good for streaming data. It's the canonical big data processor. We can accept any kind of strange behavior communicatively. If we want to communicate with someone, we'll manage doing it, even across linguistic boundaries and various misunderstandings. We have a great readiness to accept strange behavior on the part of the interlocutor we're talking with. We expect people to be fairly coherent, and we understand, oops, there's something going on with them.
Yeah, we lost your slides, you see.
Lost the slides. Let's try to reshare them. Something happened. Are they up again?
Not yet.
I'll try this trick of resharing them a second time. We need to talk about Ubuntu with the good people at Zoom. I can hear you, but connection seems to be.
Yeah.
I can share your slides from my computer if you want.
Okay. That may be a better idea, since the sound quality is better than the sharing quality. Let's see if I find a way of doing this easily. Let's see, there we are.
Share my screen with the slides.
Here's the latest version of the slides should be in your mailbox now. Let's see if that works better. Let's see if this. They might be reordered since the version you got, but we'll get through them in some ways, yeah. We skip that one just for now. Just go on a little bit. In the interest of efficiency, go through this one, and then we'll take it from there. And then I'll say ding or something when I want you to switch slides. Go on, click a few forward. Yeah, do the next one. Okay. So what I was going to say is we want to build something that will cope with this. So a representation for human information processing is a good model, and we shouldn't be too true to human processing if we're not expressly building an Android or anything. But this is something we want to have as a model, since it seems to work fairly well. A representation should have explanatory power. We should be able to ask how and why from it. We should know what it's doing, which is sort of an argument against entirely black box things. Ding. Click. It should be practical and convenient for further application, which means that we should, again, be able to retain feature structures. We should know what's in there if we want to. Ding. And we should be inspired by human performance, in the sense that if we're not processing human data well, there's something we can improve on. You can just click through the next ones here. We should be able to handle patchy data. We should be able to do this efficiently, and we should do it task independently to some extent. Next slide. And the approach we suggest is high dimensional to allow for rich representations. We should want it implemented as a vector space, and we should be able to, vector space, since it's mathematically well defined and we know how vector spaces work, and it's actually quite computationally efficient in certain ways. What we do is we use random patterns to index observations. We use random patterns because they are useful in the sense that instead of indexing stuff by one hot vectors, we can index items in a fixed dimensionality and still stay orthogonally. I will go through this in a little bit in more detail. But the main idea we have is that what we want to do is build an encoding which is useful for other further models that good people working on, say, deep learning and such are building at present. So this is our objective here, is to build something that other people can use, which is versatile enough to capture many aspects of how human communication works. Next slide, please. So distributional semantics is something that's bandied about as a trendy word in some parts of the academic research fields. And this is sort of the general idea here, that you can look at items such as these on the slide now, and you can sort of figure out, even if you didn't know English, you sort of figure out that some of these things seem to work about the same way. Click. And if you look at these things, you can sort of find stuff like this, that the word hot seems to work more or less the same way as the word warm or boiling and tepid, and more or less the same way as the word cold and freezing. And it has to do with other words that has to do with enjoying and preparing, and it has to do with stuff that may be hot or not, such as tea or meals or food and even people in some cases. Click. The way this distribution models are captured is typically done using a vector space of some sort, today frequently called embeddings. So the idea is that you take these very sparse observations of items co-occurring. If you do a co-occurrence matrix of words, you will end up with a huge matrix of mostly zeros. Most words never co-occur with another word, but the ones that do co-occur, they have something to do with each other. Now you want to generalize from those. So what you do is you take this huge matrix of mostly zeros and some co-occurrences in it, and you project it down into some sort of low-dimensional space, which allows you to generalize and allows you to save space as well. This is a way to quantify the distributional data. You can do this by, probability estimates as well, just co-occurrence estimates directly without going over the matrix. But in essence, what you're doing is you're capturing stuff that happens together, and you're doing stuff with that information, that some things happen together, some do not. And this is used in mostly today with words, and surprisingly not used in broader data contexts, such as, say, Internet of Things, where you might have sensor data and such. The word and to some extent visual image processing has been very popular in recent deep learning approaches, but there's some risk of this being very black boxed, which sort of swears against some of the principles I gave you just a couple of slides back. Next slide, please. So what we do is we use this random indexing approach, which I'll give you a computed example of in the next slide here. What we do is we give each item we see a sparse, randomly generated, let's call it a hash key or a label. We aggregate using vector addition those random indexes to get context vectors for co-occurrences, so that when we have two words together, we add their vectors together and we'll find that they converge toward a similar representation. Similarity being something we can measure by simple cosine. All of these operations can be done in vectors. What we do is we can add vectors, which gives two vectors that are more similar to each other than they were before. We can also do something slightly trickier. We can permute vectors. If we have two items of information in a vector space, we can accommodate them both within a fixed vector space by shifting one of them a little bit, or permuting the elements smartly. And this is slightly technical, but this is a neat way of, in effect, building a tensor in a fixed space vector. This needs more space than this one seminar allows to explain it properly, and some hand waving and whiteboarding to be completely lucid, but we have luckily written a number of papers on it. There were some references early on in the slide deck, which will be shared to you by Sven and Malo in a little bit. And this model allows us to have explicit feature engineering if necessary. This model allows us to accommodate co-occurrences plus other observations in the same space. This is something that's potentially hugely useful if we want to accommodate, say, contextual factors, such as what time zone is this being spoken in, how many people are there, what sort of text is this, is this a immediate response to something else, is this something large, is this something small? This allows us to put in stuff into the feature space in a way which previously wasn't practically doable unless you had, you know, a hugely growing vector space where you added dimensions for each item showing up. Next slide, please. This is what I just said, so we can skip ahead. So talking about randomly projecting stuff into a vector space sounds scary in the sense, and frequently people worry about how much does this random projection cost and retrievability, because if you have a vector space and you add a new dimension for each new item, say that you have a new word and you want to calculate co-occurrences with it, if you add a new column and a new row in a co-occurrence matrix, what you get is a crisp and neat picture of exactly what happens with that word at the cost of the representation growing immensely with the size of vocabulary. If you instead project stuff randomly into a fixed dimensional space, and this is something, this is the background for the entire random indexing approach, of course, everything may be messed up. These little blue and red graphs show what happens if you have too small a space, which is what you have to the left. If you have 100 dimensions, the red items, which are random co-occurrences which shouldn't be there, they tend to get about the same closeness as stuff that should be close to each other, the blue ones. If you add dimensionality, this shows that in a suitably medium dimensional space, you will find that it's very easy to separate random noise from the item itself. This is a very, let's say, simple way to show that random projections into a low dimensional space is nearly orthogonal and actually does retain differences between items. This is sort of the crucial empirical proof of a mathematically well-defined property of medium dimensional or high dimensional but not hugely dimensional spaces. To do the same thing that I've shown here in a 2000 dimensional space and the one to the right, with one hot vectors where you'd have zeros and just the one in the item that interests you, you'd have a space of hundreds of thousands of dimensions, which is, you know, quite impractical. Next slide, please. Here's a work-through example. Let's assume that we have two new words we know nothing about, hot and chilly. Click. We see them used in the item, the weather is hot and the weather is chilly. Now, weather has a hash key, which I've artificially created here in a 6-dimensional space. We normally work with 1,000 or 2,000 dimensions, but this is for illustrative purposes. If we add them into the hot and chilly items, we see that their cosine now is 0. They have been used exactly in the same context. They should be, you know, fairly close synonyms. Click. More data comes in. Someone says the climate is hot. Another person says the climate is chilly. Again, climate has another index vector. We add them in. What happens? They're still identical. Cosine is still 1. Yeah, go on. That's the right thing. Now someone says the weather turned hot, and someone says the climate seems chilly. There are two new items there. We add them in. Hot and chilly start diverging, and their cosine now is down at 0.45, which seems pretty bad. We would want them to be closer since they're very similar words. And this is, you know, exactly what we want. They should be identical, but they should be notably similar. This is the way we keep track of what happens. Imagine doing this for millions of documents, you know, 1 per hour or millions of documents an hour, and just adding in stuff like this. What happens is that words that are similar and should be, like hot and warm, have very similar context vectors. Hot and chilly that are slightly but notably similar, they will have cosines at 0.5 or 0.4 and so forth, depending a little bit on the various parameters in the model. Next slide, please. So the thing is that, and this is I will not go into the details here, but the thing is that in a high dimensional space of say 1,000, most random co-occurrences will be at 90 degrees. There's a very, very narrow noise corridor, if you'd like to think about it this way. You can trust me in the observation that human intuitions about how high dimensional spaces behave are not quite what you need to understand them. If you take two random spots in a 1,000-dimensional space, they will not be near each other at all. They will almost certainly be at 90 degrees from each other, because there is just so much more. There is just so much more equator than polar caps in a 1,000-dimensional space. This is, you know, a quality of how dimensionality works. And this is something that's worth thinking about. And the result here is that any angle that's closer than, say, 89 degrees is a notable event, which means that there's plenty of space to model similarity in. So even a cosine of 0.2 is a highly significant nearness in a 1,000-dimensional space. This is not something you think of, you know, without doing some empiry on top of it, and these graphs reflect that. But it's just to reassure you that the previous slide, where we're working towards cosines of 0.4 and so forth, they're quite notable. This is all you need really to think about how to build a vector space of notable similarity for items as observed in streaming text. Next slide. Next slide, please. Now, the trick here is that if you have text streaming in through your, you know, garden hose or your fire hose, there will be words coming in at a rate you cannot quite process easily. And the way to do that, the way to work with those is you keep aggregating similarities, you keep aggregating observations. Whatever model you choose, you will end up with, you know, plenty of observations. And there are all kinds of parameters you need. And this is sort of the tradecraft of distributional models, if you wish. You keep seeing these items. When are items showing up together? Next click. So what does it mean for two words to occur together? Is it important that they occur very closely together? Is it enough that they occur in the same document? This is sort of the linguistic issue. Where are things close enough to be important? Is it different if the items come before or after? Or are these the same thing? How do we distinguish the unusual and trivial words that don't seem to work towards modifying other words' meaning as much, such as, you know, words like how and from and is, or from words such as distinguish and unusual? Do we want to do this continuously? Are we really in need of online learning, or can we, you know, go off and compile a lexicon out of these things, out of what we've seen, and then we use it? This is a issue where we've taken a strong stand that we want to be continuous about our learning. But, you know, in some cases you might, you know, have a standard English dictionary or something, and then you can dispense with a lot of stuff. And do we need to handle multi-word terms? Is this something? Do we need to worry about words such as White House? Can we expect White House to be, you know, just two words, or is the White House something specific that we need to handle as a lexical item in itself? Do we need to learn these as we go, or can we list them beforehand? More importantly than anything else, we need to figure out, are we doing the right thing? Is the model doing what we expect it to? And how to model that is a hugely non-trivial issue. And there's this scary thing that if you keep learning stuff from statistical data, you end up eventually with recoding items in the same, and some very frequent items will swamp everything else. With large amount of data, you will end up with one vector for all words, which is sort of the vector for English, and you need to keep that in mind. So there's plenty of parameters, plenty of tradecraft here, and when you start building your learning model, irrespective of which exact computational approach you choose, although I strongly suggest you would want to use something with a fixed dimensionality and so forth, you will have to think about all these various parameters and experiment your way through the path of hyperparameters to get where you need. This is an observation that's general for almost all learning models today, that the exact approach you choose is not important in its qualities as much as in its processing capacity. And in the choice of these hyperparameters you select. I mean, if you take some of the standard models out there, you will end up with more or less the same result. If you take a couple of them and compare, if you do all the pre-processing, all the make your decisions about multi-word terms or how you measure your loss functions or whatever, you will end up more or less in the same result. The differences are minimal. The more important things have to do with deciding what you want to learn, what sort of semantics you're modeling, if you want to do it for entire terms, or if you want to do it for entire multi-word terms, or if it's single words, or what you're working towards. These hyperparameters are, well, like I already said, they're sort of the tradecraft of distributional models. So this is the reason people tend to today use standard embeddings packages. They will download an embedding that has been pre-trained using some standard model and use it for their deep learning needs. I'm very unhappy about this because that means that people keep using the same model or similar models for very various tasks, and they might not be the right thing. So this is a place where I should, warn everyone from using the standard packages unless you really want to just do initial exploration. It's a good idea to build your own or talk to someone who builds them and discuss what you want to model when you're doing it. Next slide, please. So here's an example of an experiment I've been building just the other day or this past week. I've been building, click please. I've taken a bunch of sentences, thousands or tens of thousands of sentences in this toy example. I've indexed them for words and also for constructional elements because I'm tracking, let's say, speaker stance in these utterances in question. And I've projected them all into the same space. Click. And here's just the probe sentence I came up with this morning just to see what sort of space there is. This is just something I pulled out of the corpus. I randomly picked it out the other week as a weird enough sentence to test for. Then I tested, find me some sentences that are similar to it lexically. This is sort of what standard embeddings would do. Click. And you find this sentence. This is similar. Then I clicked again. Then I did another search. I want to find something that, never mind the words, it needs to be similar in its constructions. And I get this other bit, which is sort of, this is exactly what I was practicing for. I wanted to find stuff that has sort of the same speaker stance in the utterance. This is an illustration of the fact that standard embedding models, which would probably give you always A, would probably not give you the model B unless you built the model to accommodate these things. So this is a way of building a lexicon, not just of words, but also of constructions. This won't happen unless you make that order for your vector space. Easy enough to do, but you need to know what you're doing or talk to someone who needs to know what they're doing. Click, please. Right, yeah, this is what I said. Click. So what we use this for, what we have been using our lexicon for, which again, like I said, it's built from streaming text using a fixed dimensionality, and it keeps learning what it's doing all the way. We use it for a text clustering tool, which you can play with at Explorer Gavagai SC. And we build a living lexicon. Currently, the count of the day, I think, is 45, it should be 45 right now. And they're both available through APIs. And the thing is here that these don't provide anyone with vector spaces, but if someone really wants pre-computed vector spaces, they should talk to us or to someone else to build them themselves. The point here is that building a vector space or building your own embeddings model is actually quite easy, but there are all those parameters I just now mentioned, and doing it, you can inadvertently end up with a vector space that models some features of language quite well, but others much less well. There's a tradecraft to it. And while there are interesting models that'll build you something that looks good, you need to sort of think about some of the parameters you're thinking about, you're wanting to model, because typically you want the embeddings there to give you some sort of effect. And you might not be getting the right effect if you have an embeddings model which gives you, say, you throw in coffee and you get back tea, cocoa, and a bit further off, you'll get milk and water, and then you might get wine and beer. That's one type of embeddings model. Another embeddings model, you might throw in milk or coffee, and you'd get back drinking, enjoying, taking a break, discussions, coffee shops, co-working spaces, that sort of thing. Those are both reasonable models, and they're an effect of how you built your embeddings model. So building a model of embeddings from streaming text will give you different sorts of embeddings depending on how you set these hyperparameters. You don't know, if you don't know what your needs are, then you probably could use just the words as they are. You don't need embeddings for that. But embeddings are built to capture context of words, and those contexts are very different depending on what those embeddings should be built very differently depending on what your needs are. This is why I really encourage everyone who wants to use embeddings, take a quick glance at why and how the embeddings model you're looking to use is built, and then reassess your needs once you understand what the differences between those models are. And if you don't have anyone available near you, reach out to me and I'll help you through this discussion, because there's plenty of stuff there that actually makes a difference, because language is a manifold thing, and there's all kinds of signal in it. Click, please. So what we want to do, instead of using, I shouldn't have written existing, but the most popular models, why are we using a proprietary model? Well, we believe that the models you want to use should always be streaming and online rather than compiling. We want to build this at real world scale. So we want to have a model which keeps learning as it goes. If you don't need that, if you want standard embeddings model, you can use, say, Word2Vec or a Globe or something similar, which will give you a compiled model, a freeze-dried one, if you will, and you can use that. But you need to know what hypothesis went in when it was built. Click, click. And this is in contrast to localist representations, which are models that are not non-embeddings models, if you will, or compiling models, which are models that require you to batch stuff and then, redefine and redeploy, which we don't quite like. We want it to be online. And we don't want things to be end-to-end black boxes. We want to be able to examine what goes in and be able to trace it as it comes back out. This is not true for all users, though. So another embeddings model will give you an end-to-end black box, which might be exactly what you need if you know what that black box is doing from an eagle's eye view. Click. So what I want you to remember is that handling hypotheses and providing explanatory power are important, and computational habitability is important. Neither of those are optional. You should know what you're doing. Even if the hypotheses are not yours, you should know what model you're using. If you're building, say, a deep learning machine to categorize customer feedback or something, you want to know what the embeddings you're using as a basis are built for. You also need them to be efficient. Neither are optional, and a good design encapsulates both. Click. Feature engineering is a useful method to understand the world. This is sort of how we get learn. And some people who work with machine learning use feature engineering as a negative term, as something that should be avoided, that the system should learn by itself. I don't subscribe to that view, because I think this is the way we inject hypotheses into the model and are able to see what's going on. Knowledge representation should support it and declare what sort of features are being used. If it's an entirely black box, you should avoid it. Be careful about it. The things that are optional are, we don't need to build a brain. We can build something that's probably better than a brain. We don't need to build something that's explicit. We might have a completely opaque model, as long as we know what hypothesis went in when it was built. So that's sort of the third bit. The fourth bit, that's probably not on this slide, because this is, right, there it was. Yeah, we have APIs, and we're very happy to, help out both commercial enterprises and academic exercises, which are, have sort of different needs. But if anyone is interested in embeddings models and wants to work on building their own, call me up. We have ways of doing this. And there are plenty of interesting other models out there that are, in my view, less useful in some ways, but which are quite efficient and versatile. But you need to know what hypothesis went into it. So that's the number one point here. Ask for your embeddings. Why are they built? What sort of assumptions went into it? What sort of presumptions of human communicative behavior are there before you start building your entire enterprise on top of one of them? Thank you. That's more or less what I wanted to say.
So before I ask you questions from the audience, I need to dig into the chat a little bit. I have a question of my own, which is how robust is so you're training this model using streaming data. How robust is the model to the order in which you see words? Is it the case that I need to first train on a standard vocabulary before adding some more interesting words, or can if I see the text in any order, it will give me roughly the same result?
It will end up in the same space. That's not entirely true because the weighting depends a little bit on what it has seen. So if you have this very specialized text on, say, ocean sail competitions, some of you probably are following such at this moment, or soccer, which some of you are preparing to follow in a little bit, then you will, very quickly learn that, soccer and umpire and field and goal are really boring words that occur in every text. And that's difficult to get away from if you then add standard English afterwards. So it's probably a good idea to initialize your system using a standard outtake of, say, news or some sample of social media text or Wikipedia or some such, so that you get the basic statistics in place and then add your own specialized vocabulary on top of it. But in general, language is surprisingly robust in this respect. So the basics of language are similar, irrespective of topic, domain, genre, style. The building blocks are very, very similar. And this is true for all human languages. We find that our model, the way we use it and the way other people use similar models, they work more or less as well for every human language.
Thank you. There was a question from the audience about class imbalance. So how do you deal with that in this model? Is it built in, or do you need to pre-process your text for class imbalance and overrepresented words? And as a follow-up, are pre-trained embeddings useful when you have small textual data sets?
Okay, those are two different questions. Let's say the first one, class imbalance in the sense that some words are very frequent and thus less informative than others. They may have a structural role in utterances, but rather little topical role or and such. This is something that you really need to address. And there are, fairly robust models, simple and robust models to do this. It's slightly more challenging in a streaming context because the first few words, this goes back to the soccer example just now. But yes, you need to address weighting and to understand what items are important and what are not. And this can be, even a simple weighting scheme will improve your results greatly. But this is an important question, and some approaches throw out large swathes of human expression entirely because they seem to be very, across the board uninformative. Others capture them and use them as bits to understand better what other items are there. This is a tricky thing, but even a simple weighting scheme that weights down very frequent items will improve your results greatly. And now again, what was the second question?
The second question is a little more technical. If you have only a small data set, would you recommend in that case using, pre-trained existing embeddings?
Oh yeah, absolutely, because the pre-trained embeddings will, and if they're well done on a large enough sample of text, in effect that will boost your small text set. That will sort of give you a leg up, like if you had read a lot of text beforehand. If it's done in the right style and right language, it's better. But I mean, obviously it should be the same language, but if it's, if you're processing social media and you train a big model on Wikipedia, it will still help. Not as much as if you had exactly the same text, same type of text, but it will still help. Absolutely. It'll give your system, it's like if a human reader encounters a new text. If that human reader has read plenty of other text, it'll be helpful than if it's someone who's a novice and, in a strange language. But again, a warning finger about using the wrong set of pre-trained. If the embeddings are trained to build synonyms and what you're doing is topic modeling, then the embeddings will not help.
So use embeddings, but carefully, and verify the assumptions that were used to build them. Exactly.
Verify the assumptions. And if you don't know what they are, call someone. There should be a hotline for this.
Embedding hotline. That's a good idea. There's a question more about Gavagai that I think is interesting. What about words that have different meanings or even different semantical structure? For example, nail as a noun and nail as a verb. So I can nail something or I can paint my nails. And those words are very different in terms of how they're used in certain contexts and in terms of their structure. So how do you deal with that?
Well, this is a problem that's common for all statistical distributional models, because taking those two examples, the one item will have very different distribution from the other item, but since they're sort of indexed together, they will be conflated in the model. Now, if you have a suitably high dimensional model, those directions of similarity will be separable in that space. So you will be able to see that nail has certain relations that have to do with, say, nail, I don't know how, I'm thinking about the noun now. Okay, there'll be nails and screws and bolts. There'll be nails and fingers and hair and various grooming things. And then there will be the direction of the verb. There will be nailing and fastening and establishing and building and that sort of thing. And those neighborhoods will be in themselves dissimilar to each other. So the one, we like to think of them as filaments in a semantic space. So if you just do a very simple nearest neighbor search, then you will not be able to distinguish between these items. But if you do a second order similarity search, then you'll find that the one set of words will be going in one direction, and they're not similar to the others. So establishing and building are going over in one direction, screws and bolts and things are here, and nails and grooming and eyebrows and other things are over here. And the eyebrows are not very similar to building, even though they both have a common neighbor. This is actually, computably doable to separate them in most embedding spaces. You need to just sort of do a second order model on top of them.
Thank you.
If you have a high enough dimensionality, that is.
So that's a perfect segue to, take as the last question, which is, how does the dimension of the space, how do you trade off the dimension of the space with the size of the corpus and the precision? Is it the case that with a large enough space, you can process a very large corpus and kind of it doesn't scale up with the size of the corpus without losing too much precision? What are the trade-offs there?
The trade-offs are, more or less the way the question was formulated. If you have too small dimension, you're compressing stuff and you'll end up losing information. If you're a large enough corpus, given the near orthogonality of the random indexing or whatever model you're using, you're not compressing things. Now, the interesting thing about semantic spaces is that it's only the near neighbors that are interesting. The fact that something is a distant neighbor is uninteresting. There's sort of a semantic horizon. So if you end up with stuff, it's not interesting to model the similarity between pencil and, cup of cocoa or crater on the moon. There might be a geometric, angle between the vectors, but it's not interesting once you get, if you start with pencil, there are some writing implements and intellectual tools around it. If you go beyond that, it's not interesting. And the point is, you need to have a large enough dimensionality to accommodate very separate local contexts. The global dimensionality is not that interesting. There's a fair bit of interesting mathematics that should be worked out by someone who's a better mathematician than me, but there's again, our intuitions don't quite cut it here.
Thank you, Jussi. Thank you for the great talk and answering those questions. And attending this webinar. I hope everybody liked it. Of course, I might have missed one question or two buried in the chat. If that's the case, we'll try to tackle that when we publish the video. So thank you to all. Thank you to Jussi for giving this talk, and see you next time. I just want to do a little bit of promotion for our next talk. So we try to vary a little bit what we present, from the more state-of-the-art things to the more technical and hands-on things. So next week we'll have a talk by Emmanuel Mason from Insights AI about how to bring NLP and computer vision together to solve common problems in both domains. And I'm very much looking forward to that too. So thanks to all, and keep in touch.